Thank you. First of all, I'd like to thank organizers for inviting me to this nice conference, and also for giving me the opportunity to talk our very preliminary result. So this is a purely theoretical work, and my history of working on this topic is quite short. And I was originally working on the cold atomic physics, and along this line, I started to interested in the optomechanics in terms of quantum classical interface, and also quantum nonlinear dynamics, and also quantum control and measurement of cold atoms. And with this interest, the work I took today is based on two underlying streams. So one is a bottom-up approach to the cavity optomechanics, which is center of mass motion of atoms as a movable mirrors. So it is a contrast to the top-down approach of using the usual moving mirror or membrane inside the cavity and so on. And I will combine this bottom-up approach to the cavity optomechanics with the atom optics of atomic ensembles, especially the cold atoms, degenerate atoms. So there are excellent experimental work about the optomechanics of atoms so far. So inside the cavity, Aspermeyer's and Kimball's group trapped the single atoms, and they observed the strong couplings. And also in the Stamper-Kurn group, they trapped thermal gases in the cavity, and they observed the optomechanical coupling and optical dye-stabilities. And also, unfortunately, we missed the talk by Berneke this morning, but they trapped the BC inside the Fabry-Perot cavity, and they also demonstrated that condensate mode, I mean the lowest order diffraction mode of the condensate, can couple with the cavity field, and it behaves like a moving mirror. So my talk today is very simple. So first goal is simply extend this condensate version to the cold fermions. So everybody asks, why fermions? So it sounds a little bit weird, because usually in the cavity QED experiment, they use both condensate, because we can use both enhancement, and it has same quantum statistics with photons. But in contrast to this advantage of both enhancement, in the bosonic condensate, there is cold collisions, I mean atomic interactions. And actually these atomic collisions suppress the effect of atom field interactions. So this can be sometimes a disadvantage to use bosonic condensate. So on the other hand, for the spin polarized fermions, in the low, ultra-low temperatures, there is no atomic collisions. And for, in order to observe the purely atom field interaction, this can be the advantage to use the fermions. And also, purely for curiosity, atom optics using fermions is less studied. So I just want to make the theory complete, both for bosons and fermions. And with this kind of motivations, there are several works about the atom optics of fermions. So one is clocks. So because when one uses the bosonic condensate for atomic clocks, there is a collisional shift. So in these papers, they suggested to use fermions instead of bosonic condensate in order to avoid the frequency shift. And also, fermions can improve the sensitivity of interferometers. And in these papers, they asked if the bosonic four-wave mixing can occur in the fermionic degenerate Fermi gas. And the answer is yes. It's not experimentally observed, but there is a similar or complete analogy between the bosonic four-wave mixing and fermionic four-wave mixing. And also in these papers, they suggested to use fermionic degenerate fermions in the cavity QED and see what happens in the usual cavity QED setup. So, outline of this talk is like this. So, main question is optomechanics of fermion feasible? And in order to answer this question, I will derive the effective Hamiltonian and show the signature of optomechanical coupling as bistability. And we will show the noise spectrum at the last. And to tell the answer first, the answer is yes, in principle. Experimentally, it might be a little bit challenging, but theoretically, we found the complete analogy between the bosonic condensate and degenerate Fermi gas as the optomechanical systems. So this is a typical setup. We can start from the single atom chains coming model. So we trap atoms, two-level atoms inside the cavity, and it's pumped with the rate eta and frequency omega L. And there is a standing wave with the wave number capital K, and we suppose that environment temperature is absolute 0. And here, cavity length is fixed as L. And omega C is the empty cavity resonant frequency, and omega A is transition frequency of the two-level atoms. And we quantize the atomic motion along the cavity axis. Here I wrote x direction. And we made the dipole and rotating wave approximation for the James Cumming model. And later, we assume the large pump atom detuning. So in this case, we can adiabatically eliminate excited electronic state. So far, I didn't say anything about the quantum statistics, but if we have many identical atoms and it's cooled down to the low temperature, we have to take into account the quantum statistics. So in the usual cavity QED setup, the only internal degree of freedom is irrelevant. So if you have one photons, and then the atom absorb and emit photons, and it makes Rabi oscillations. But it's cooled down to the low temperature. We have to take into account the centermost degree of freedom. So if the photon has a momentum h bar k and absorb this photon, then atom undergoes the momentum kick associated with absorption and emission of photons. So we will now take into account the quantum statistics in the formulation. So we have many atoms. So with the Hamiltonian for the atom and atom field interaction is written in the second quantized form like this. So the first term is momentum kinetic energy, and the second term is atom field interaction in the dispersive regime. So here I already eliminate the internal electronic excited state. And C is the field operator, and here we assume that the number of photons inside the cavity is not so large and expand the field operator in terms of frame waves. And this is valid when the number of excitation is small. So here we impose the bosonic or fermionic commutation relation for the F operator. So F, here F can be either bosonic or fermionic operators.
So do we assume there's some additional trapping?
Yes, yes. Here we suppose that we trap the atoms in the very, very shallow harmonic trap, and we neglect for simplicity. So now we like the single mode cavity photon annihilation operator C and atomic field operator F sub k. And k is the momentum of the atoms. Then Hamiltonian for two-level atom and field in dispersive regime is written like this. So first term is just a summation of the each kinetic energy of each atoms, and second term is the cavity, and delta is the effective cavity density, and U0 is maximum depth of optical potential. So this is this arises from the adiabatic elimination of the internal excited state, and G0 is the original single photon level frequency which appeared in the James-Cumming model. So the last term is very important. It's the atom field interaction, and if you closely look for this term, it annihilates the atom at the momentum k and create the other atom at the momentum k plus 2 capital K. So 2 capital K is twice of the wave number of field. So here we compare the underlying picture of the Hamiltonian with Brennecke's work and our work. So this is a ground state for cold bosons and cold fermions. And here we assumed that bosons are ideal gas, and I didn't include the atomic interactions for simplicity, but actually for bosonic condensate there is a broadening around this momentum curve because of the atomic collisions. So if we ignore these collisions, the ground state of the bosonic condensate, it just looks like this. So all the atoms, almost all atoms, are condensed into the momentum zero mode. And on the other hand, for fermions, because we have a spinless fermions, it occupies from the minus kf, this is a Fermi momentum, and to Fermi point kf. And occupation number is must be unity because it's fermions. So we have the atom field interaction like this form. So if you operate this interaction Hamiltonian into this ground state, the lowest order momentum side mode excitations look like this. So if you start from the completely condensate mode, it absorbs 2k momentum, so it occupies a momentum side mode, right and left momentum side mode. And similarly, for fermions, starting from this fermionic degenerate mode, you have to remove some atoms close to the Fermi point, and then put these fermionic atoms to momentum side mode. So this is a review of the bosonic effective Hamiltonian. So if you take into account this atomic field interaction in the lowest order momentum side mode regime, then the bosonic effective Hamiltonian looks like this. So this is a result of the Brennecke's work. So first term is the momentum side mode, this kinetic energy term, and omega rec is recoil energy. And the point is this term. So momentum side mode coupled with the number of photons, just like in the optomechanical coupling. And G is normalized like coupling constant and square root of the atomic numbers. So what happens for fermions? This is our main result or first goal of this talk. So in order to derive the effective Hamiltonian for fermions, we first define the collective density operator like this. So this is the summation of these each momentum side mode excitation around the Fermi points, and we just divide this summation of momentum to the plus term and minus term. So this is first term is a summation for minus k, and this is a positive k. And the point is that the particle and whole, pair of particle whole, correspond to bosons because fermion and fermion is equal to bosons. So this is bosons. So rho is a bosonic operator. So this is just a collective density fluctuation operator, and it satisfies the relation something like this. And by using this rho minus and rho plus operator, we can define the new set of operator, which is called B here, and beta is just a normalization factor in order to B satisfies the standard bosonic operator. So here we have plus P mode and minus P mode, and actually we have the P equal to 2 capital K, so P corresponds to 2K. So by defining this new set of operator B, now we have the standard bosons, which is a superposition of the paired particle and whole excitations. And here we make another approximation. Because we are considering the low photon number regime, the number of excitation is quite small. So in this case, the original atomic dispersion relation is quadratic, but around the Fermi surface or Fermi point, we can approximate this quadratic dispersion relation as a linear dispersion relation. So original kinetic energy term of the Hamiltonian can be approximated as the Fermi velocity times h bar and k. So with this approximation, but the important thing is that the width of the particle whole excitation, so I mean the width of the excitation numbers around the Fermi point should be much less than the wave number of the cavity field. And also this 2K must be smaller than Fermi point. It is clear from this pictorial picture. So with these approximations, we eventually found the effective Hamiltonian for fermionic degenerate Fermi atoms. So starting from the James-Cumming Hamiltonian and second quantize it with the fermionic field operator and approximate the quadratic dispersion relation as a linear dispersion relation and defining the collective density fluctuation operator, we arrive at the Hamiltonian something like this. So first term is the cavity field. This is a usual single mode cavity, and the second term is the effective moving mirror, which is made of the collective density fluctuation of fermions. And the third term looks like the cavity mirror coupling in the typical optomechanical systems. But now we have independent two modes, which correspond to the right excitation and left excitations. And effective mirror's frequency. So here we now call the mirror as a fermionic excitation. So effective mirror frequency is defined by two Fermi velocity times cavity wave number and coupling constant. Here optomechanical coupling constant is defined by the original atom field coupling divided by the some normalization factors. So the main, our main result is that fermionic collective density oscillations behaves as the moving mirrors in our approximations. So in order to demonstrate the evidence of the optomechanical coupling, so I just show the optical biostability can be visible in our fermionic optomechanical systems. So let's define the quadratures of mechanical cosine mode, which is defined by the sum of the right and left excitation position operator, and also a momentum operator is also defined as a summation. So there exists a sine mode which corresponds to x plus minus x minus mode, but it's very small, so here we neglect it. So we consider only the cosine mode here, and x plus minus and p plus minus is defined respectively like this. And then we can now follow the standard theoretical approach for the cavity of mechanical systems by write down the Heisenberg-Langevin equation for the mechanical position and momentum and cavity mode. So here we assume the absolute zero temperature. There is no mechanical damping. So now we have only Markovian noise for the cavity field. So it's written like from the input output theory like this. So optical bistability is typical evidence of the optomechanical coupling, which is first observed by the famous work by Volta, and you know very well. So it behaves, it exhibits a hysteresis as a function of input and output power. So recently, also in the bosonic condensate, this is an experiment from Esslinger's group, and this is a work for the cavity of mechanics with the Bose-Einstein condensate. And in this work, they also observed the Hamiltonian in the very low photon number regime. So as expected, we have for the stationary state from the Heisenberg-Langevin equation for fermions, we have the cubic equation for the cavity field C. So by solving these equations, we have this kind of bistability behavior as a function of pump rate, and this is a photon number, and this is something like phase diagram where bistability exists. And here we assume the parameter like this. So cavity length and optical wavelength and cavity damping rate is taken close to the Esslinger's experiment, and pump and atom detuning is defined like this, and these are coupling constant, and M is a typical orders of magnitude, and number of fermionic atoms is 2 times 10 to the power 4, and wave number of optical field over Fermi wave number is equal to 0.1. And the important point is that these parameters are consistent with the assumptions we already made, which is linear dispersion relation, and also number of excitation is also small. So it means that even if we start from the fermionic condensate, we can expect that the optical bistability can be observed. So we can also solve the linearized Langevin equation. So this is written like this, and this is solvable in the Fourier space, and from these equations we can obtain the noise spectrum. And I don't tell much detail about the noise spectrum, but so we can write down the mirror noise spectrum and detectable cavity spectrum, noise spectrum, where denominator is written like this. So later I have to analyze this form of noise spectrum. So as a short summary, so we showed that fermion's low-lying phonon mode is collective density oscillations, and which consists of particle Hall excitations, and this is coupled with cavity field as the optomechanical form, like the Bose-Einstein condensate in the cavity. So future directions include the measurement of atomic collective excitations, and also this is not restricted for the atomic case, but I'm also interested in the quantum nonlinear dynamics can be tested in the cavity optomechanical systems. And in this work, we made the approximation that the number of excitation is quite small, but in order to generalize our theory, we have to go beyond the lowest order deflection regime. And maybe this is a little bit weird project, but our system is made of the particle and Hall pair particle-Hall excitations. So this is similar to the exton-polariton systems. So we might be able to extend this formalism for the exton-polariton optomechanics, including the Coulomb interaction or binding energy between the particle and holes. So this is what I'm doing right now, and it's ongoing work and no result yet. But anyway, so we have to decide the cavity field, dynamics of C and C dagger and atomic field consistently. So in order to do so, starting from the master equation and by taking the average value in terms of the coherent state, we can represent the master equation in the Q representation or Fushimi representation. And then master equation can be written exactly like the C number equation, which is similar to the Fokker-Planck equations. And by solving these equations, we can know the full quantum dynamics or self-consistent dynamics between the cavity field and atoms. So finally, I would like to thank the organizer and my former boss, Pierre, for the collaborations. And this work was done by visiting occasionally to the University of Arizona. And I would like to thank Mishka, and Swati, and Daniel, Wenju, Greg, and Steve for hosting me and discussing while I'm staying in the University of Arizona. Thank you very much.